Hello, everybody. How's studying going? Anybody taking the test yet? Let's find out. Oh, a couple people. Oh, look at you guys. Crushing it. Absolutely. Initial grades, everybody who's taken the test has gotten a B or better, a lot of high A's. So, I don't know if you guys know that already. Does it tell you ahead of time? I don't know. Well, those of you who are go-getters are doing well. I'm proud of you. So, if your parents never told you that, that's what I'm here for. Easier than the first one. All right, fine. I'll make the third one the hardest then. That's all you. All you, buddy. Um, okay, sorry. I'm just reviewing this PowerPoint that I'm about to give you to see if there's anything that I'm like not 100% on and might need to refresh on. Because I am prepared for class, obviously. So I hope you are more prepared for class than I am. All right, I don't know that we're gonna get through all of this. Hopefully, okay. I'll break it up. Let's see, where should I break it up if I was going to break it up? Inspiration. Let's see what's the name of that one. Um, I think we can do it. Let's do it. All right, who's ready? Learn some stuff, or to space out and watch this recording later. Recording? Recording. I am recording, right? Yes. Meeting, recording, in progress. Great. All right, here we go. Who is ready? I've been told that the pace of this class is way too slow, so um, let's speed it up. All right. So, housekeeping stuff before we begin. Okay. So, nothing's due this week. I'm also behind on updating that syllabus stuff that I told you I was going to do and I lied about. But nothing due this week, obviously, except the test in this class and in lab class. So, today we're going to do intro to the lungs and the respiratory system. And then in lab, we're going to go over the histology and all that stuff, intro stuff. And then because I'm a nice person, no class on Thursday. Okay, so don't worry about showing up here Thursday at all. Two reasons. Number one, I have to work. Number two, I don't want to get like too far ahead again. So we're gonna space it out again, and where there's nothing to review. So I'm not gonna host a review session for 3 people who are gonna take the test Sunday night. So in order to kind of keep on track, we're just gonna have a day off and party. And Hurricane Day, right? Like, I don't know, maybe the school's closed. Let's go with that. Fun fact, I just moved from Florida, and so this doesn't scare me at all. I was talking to somebody at work, and they were like, well, it gets really windy and the trees fall over. No, they don't. No, they don't. Not compared to where I lived, which was Pensacola, Florida, and my septic tank collapsed one time. That was fun. Okay, less about me, more about you. Respiratory system. Arizona and not excited about it. It's literally not a big deal. We're gonna be fine. Respiratory system. Let's move on. Why is this not working? What are you doing? Click, click. Did I have a failure? Oh, a laser pointer? Oh, okay, hang on. No, that's wrong. How do I, can I color? Oh, that dude. Oh, please. What's this? Screen intro. Hold, please. I still haven't figured out how to draw, so. I would like to draw. Do I need to do something else? No. Great. More pages. Content. Shape. Okay. It's less important. Yeah, it's less important. So it's not a big deal. I'm just going to use my clicker again. So maybe I'll do the laser pointer. That's easier to see. How about that? All right. This is mountain climbers. Cool story. All right. Function of the respiratory system. So it is to gas exchange. Number one is gas exchange. That's the most important function of the respiratory system. It does that by physics mostly. So it's in order to increase the amount of physics that's taking place, we have to increase the surface area, right? So more surface area, more physics, okay? Your lungs, fun fact, if you were to take all of the surface area and lay it like one cell thick so that just only the exchange area was out flat, it would cover a whole tennis court. Isn't that so cool? That's in your body. Okay. Move air to and from the exchange surfaces of the lungs along the respiratory passageways. So you're moving air from outside your body to inside your body. Okay, pretty simple. Protect respiratory surfaces from dehydration, temperature changes. All this is to say that there's some barrier defense in it as well. Okay, so you're not just bringing like outside air, exposing it to your skin directly and exchanging gas right there. That's why we're not frogs, okay? There's functions within your respiratory system that protect your lungs, basically. And also things like temperature changes. Your lungs actually, the turbidity of the air moving into your lungs heats up the air so that you're not like shocking the system too. So you're protecting that surface area in a couple different ways. And you're also creating a hospitable environment for all of that exchange to take place. Okay, physics, we'll get there. All right. Producing sounds involved in speaking, signing, and other forms of communication. Weird sounds. Okay, you do all that because of your respiratory system. And then also facilitating the detection of olfactory stimuli by receptors in the nasal cavity. Lots of words. Okay, you're smelling stuff. That's pretty much what that is. Okay, the smell, and we'll get there, works by picking up chemicals that are floating around in the air. So when you fart, small chemicals come out your butt. They float through your pants and up into the air. And so when you smell that, you're smelling butt chemicals directly. Fun stuff. Same thing for like any other smell. If it's a smell, it's chemicals that are being excreted by something else, and your nose is just picking it up, and you're getting those molecules bouncing around in your nose. Okay? So that all happens by smell. All right. What are we looking at here? Major respiratory structures. Okay, here's the thing. Here's my disclaimer about anatomy. It's anatomy. Everything in the human body is fair game, right? So I want no emails about what do I need to know on this picture, whatever. Be able to look at this picture and relabel it completely from scratch, okay? So let's start with, we'll just do like the pathway a little bit. So air, and for this purposes, we know that we breathe throughout our mouth as well, but let's just stick to the nose, okay? Because mouth, we're going to get in digestion, and we'll talk about the mouth in extensive detail. But for now, let's stick to just breathing through your nose, in and out, okay? I just breathed it through my mouth. I'm so sorry. All right, so air is going to come from here, outside your body, and it's going to go up into your nostril, right? Your nostril is the hole, okay? From there, it's going to go into your nasal cavity, and you have this extensive structure within your nose. So it's actually this big. It like takes up a lot of space. You would be shocked. It's not just like a nose hole and then straight down to your mouth. It's like into your face. All right. So you have all of this structure right here. Okay. From there, it's going to move down into the pharynx. It's going to share some space with the digestive system, and then it's going to move down into the larynx. Okay, and we're going to get a little more in depth with these structures, but for the most part, it goes down into the larynx, into the trachea, into the left or right main bronchus, and into the lungs. Okay, these are lungs. All right. All of that is facilitated by the diaphragm, mostly. Questions? No questions. Got it. All right, upper respiratory tract. So that's your nose, your nasal cavity, your paranasal sinuses, and your pharynx. So everything from here up is your upper respiratory tract. Okay. All right, your nose. So from surface anatomy, you have your dorsum nasi, that's the bridge of your nose, right? And then you have ala, which are these little things that flare, and then your apex, which is right here, and then your philtrum, which is this thing right here. Okay, this little like weird thing between your upper lip. All right. From a bone standpoint, you've got the frontal bone, which is this, and that's important because there's sinuses up in there. You've got your nasal bone. So if you notice, your nose is not all bone, okay? You have the nasal bone, and then you have cartilages, okay? So that's why if you look at like a picture of a skull, it's just a weird hole because it's not bone, that's cartilage, okay? So you've got your nasal bone and your maxillary bone, which are right here, and make up the bones around your nose. And then the cartilages are the septal cartilage, which is this first one, your major alar cartilage, which is this one. And then this is also septal cartilage below. So like if this is connected, this is kind of sitting on top of it. Like the reason you can go like that, right? But you can't really do that with your septal cartilage. All right. Upper airway. Okay, so it really bothers me how this is reversed because we have everything the other way. It's fine. All right, so air goes up in your nostril into the nasal vestibule. Okay, so vestibule, just another word for like a garage or something like that. It's just a space out in the lobby that the air is hanging around in. Okay, now from there you have conchi or conche or conchi, whatever you want to call them. And these are these regions right here. They're ridges. So if you were to take somebody and place them head up, basically, you'd have like these little ridges like this, okay? They're like, think of like ledges within your nose. And what this does is it creates like a labyrinth that the air has to travel through. So more surface for it to hit, more warming up that air, okay? So all of that takes place in the beginning of the upper airway, okay? So the bumps, these ridges are called conchae, and then the ravines between them are called meatuses, okay? So you have a superior, a middle, and an inferior meatus. So the air is traveling through the meatuses between the conchae, okay? All right, so one other thing up here. So if this is your frontal bone, this is your frontal sinus. So the air will go into the sinuses as well, and then sphenoidal sinuses. So more surface area that the air can kind of travel through. And you also have a bone right here called the ethmoid bone. If you notice, it's not like broken up like this. These are actually holes. So there's holes within your ethmoid bone. And the reason for that is because your brain sits right here. And the olfactory bulbs sit right here. Okay. And those put little ciliary bodies down into here to pick up smells. Okay. So fart smells come up here and they touch the sensors right there, the neurosensors. Okay. Neurons. All right, sensory neurons. Okay, so that happens right here on the ethmoid bone. And this is olfactory epithelium right here. So this layer of skin is epithelium and it's epithelial cells right there, okay? So air comes up through the meatuses and past the pharyngeal tonsil and the opening of the auditory tube. So the auditory tube, this is what, when you go like that, it's connected to that. Otherwise known as the eustachian tube. Should we shame Dr. Eustachian? Let's see. The eustachian tube. Oh, this guy's actually kind of cool. And he's Latin. All right. Everybody's favorite game. This is Bartholomew Eustachi. He is not British, so I'll give him that. He's Italian. He's got a cool name. He hung out with Leonardo da Vinci, I think. All right, so this is what that's called, also known as the auditory tube. Why? Because we don't name things after people. All right, we name them after anatomy. Okay, so auditory tube right there. That's why you can, because it's all connected. All right. All right, then air goes into your nasopharynx, and not much happens. It goes down behind your digestive system. And we're going to pass over all of this stuff right here because we're not there yet. And then it goes into your oropharynx, so nasopharynx. So if this is all pharynx, this is your nasopharynx and your oropharynx, right? And then your laryngopharynx, okay? So air goes down the pharynx and then boom, into the trachea. How? By this. Wait, where is it? This right here. This is called your epiglottis. So your epiglottis is a piece of cartilage that controls whether you're breathing or eating, okay? And it flaps back and forth, and we're gonna get there. But it basically closes off your airway so that you don't end up with food in your airway. If you end up with food in your airway, you die, okay? So that's all controlled by your epiglottis and your hyoid bone right there. And then you go into this area right here, which is your vestibular folds and your vocal folds. So your vocal cords, same thing right there. And that passes through your vocal cords into the area between your thyroid and your cricoid cartilage. And then it goes down into your trachea major. Not really, it's just trachea, okay, from here on down. Okay. Other things that are around this area, you've got your thyroid around there, and you've got your esophagus around there. So, test question. Is the trachea anterior or posterior to the esophagus? You don't have to answer that. It's anterior, obviously. That's not a test question either. That's way too easy. All right, we're gonna go over this a little bit. Great job. I'm mostly going to skip over this though, okay? Just know that respiratory epithelium is pseudostratified ciliated columnar epithelium. That's important. It's pseudostratified, it's ciliated, it's columnar, and it's epithelium. All right. Divisions of the pharynx. So we talked about the nasopharynx versus the oropharynx and all that. So if it's all divided by your palate, okay, so your hard palate is this hard bony part right here, and then your soft palate is mostly cartilage and it kind of moves around. All right. So everything superior to your soft palate is nasopharynx. Everything at or inferior to your soft palate is oropharynx. And then where your epiglottis is, everything around that is laryngopharynx. Okay. Naso and oropharynx are the big ones. Okay. Lower respiratory tract. Okay, so we talked about the epiglottis. This is just a thing that flaps back and forth, and it protects your lungs. Okay, it's a very good thing, and it keeps you from choking and dying. Okay, that is held in place by the hyoid bone. So the hyoid is this thing right here. You can feel your hyoid. It's like right there. Fun fact: when you let's see, I want to make sure I don't do this backwards. When you unalive yourself by looping around, generally speaking, it breaks the hyoid bone. When you are unalived by somebody else, generally speaking, it doesn't break the hyoid bone because versus this. Okay, so on an autopsy, you can tell it's not like a 100% exact science, but you can tell how somebody died based off of where the injury of the hyoid bone is. That's just a fun fact for you. So all that to say, Jeffrey Epstein did not kill himself, according to the pathologist. So body of the hyoid bone, right? And then there's horns, right? They come off right there. All right, and then we have membranes kind of between that. So you have this thyrohyoid membrane. Here's the thing about this whole area, okay? If you have something that has two connection points, it's generally one connection point and then another connection point and then what it is. So like there's muscles all up in here. I don't think we have to learn them. But there's like thyrohyoid muscle. Like that's a thing. And it's just the muscle that's connected from the thyroid to the hyoid. Okay. So thyrohyoid membrane is the membrane between the thyroid and the hyoid bone. Okay. The thyroid is cartilage. All right. All of this is cartilage. And in the middle, right here, where this kind of dips down, this is called the laryngeal prominence. It's right here. That's your Adam's apple. But we don't name things after old men. So it's your laryngeal prominence. I don't know who Adam is, but I'm willing to bet he doesn't deserve to have something named after him. All right. Then you have your cricothyroid ligament. So there's a ligament right here between your thyroid and your cricoid cartilage, right? And then your cricotracheal ligament. So you have a ligament between your cricoid cartilage and your tracheal cartilage, okay? So if there's a ligament or a membrane between, it's top and bottom ligament. Top, bottom ligament, okay? Or bottom top, whichever one, okay? So this is an anterior view. This is from the right lateral. So you have your epiglottis, right? And then you have, let's see, vestibular folds. Like this is within that space. So think of like a tube almost. So within that, you've got vestibular folds right here, and then your vocal folds right here, okay? And all of that is protected by this, like all this cartilage stuff. So you have your thyroid, you have your cricoid, you have your arytenoid, your corniculate, cartilage, and then your cuneiform cartilage kind of sticks off there. Major ones, I'm going to say epiglottis, cricoid, thyroid. You don't need to like necessarily know like corniculate or like all of these are the little tiny ones that aren't in bold, but just kind of know like where they are. Okay, so if I tell you, like if I ask you like where's the arytenoid cartilage, don't be like it's in your toe, because that would be stupid. Okay, so all of this, right, and know like what if I get a good one would be like which of these is not a cartilage found in the larynx. Since there's like 4 of them, okay? So that's the larynx, voice box, okay? Vocal cords. So if you were to take a scope and stick it like that and go, ah, And I encourage you to ping your significant other down tonight and tilt their head back and say ah, and then stare in their face hole. You would see this. You can also just go to YouTube if you really wanted to. So you've got your esophagus in the back, and then the anterior side is going to be your trachea. So your true vocal cords are this part right here, and then your vestibular fold is this like red meaty thing, okay? And then you have your glottis, which is right here, and your epiglottis, which is just going to flop back and forth. So make them hold their mouth open, say ah, and then swallow. And while they hold their teeth apart, they'll love that, okay? If you don't have a significant other, do it to your dog. And then you have your tongue right here, okay? So this is all in the same like area. So if you kind of go like that, you can go straight down all the way to the lungs, like sword swallowers. All right, trachea. So larynx is right here. Trachea is right here. And this is made up of cartilages. So these are like rounded circles. Okay. What would be a benefit of having rounded circular cartilages holding your trachea open? Better airway. Yeah, it holds it open. Like you don't have to force it, right? Like it's just a PVC pipe that's open. Think of like, have you ever tried to breathe through? I don't know if you have, like a hose that keeps collapsing or something. This is held open, okay? Because you're going to create negative pressure right here. So you need this. If you create negative pressure, it would just collapse. So you need to have something holding it open. So remember that the tracheal cartilages are you have a whole bunch of cartilage and stuff over there because you need to hold that space open. You can't just let it collapse on itself like the digestive system, okay? So you have all of that in place to kind of create a space that you can get air to the lungs. All we're worried about right here is getting air to the lungs. That's the most important thing, okay? So from there, you have your trachea, you have primary bronchi on either side, your right and left main bronchus, and then you have secondary bronchi on here. So that's that second bifurcation right there. And then you tertiary bronchi. And each one of them has a name. There's 19 of them, and I'm not going to make you memorize them because I'm very nice. Okay, just know primary, secondary, right and left. Okay. This is a picture of goo, and I will show you it in lab. Any questions about the lungs or trachea so far? Seeing none, I will move on. Okay, the lungs. How do they work? What are they? Are they real? Yes. So, gross anatomy of the lungs. So you have your trachea and your bronchus, right? This main primary bronchus, okay? Then you have secondary bronchi, okay? And then segmental tertiary bronchus. And there's 19. I'm not going to make you learn because I'm a nice person, okay? And this is within the airway, okay? So air comes in, all right? And then it eventually gets to a point where gas exchange happens, and then the rest is within the body. Okay, so we're going airway in and then body in. We're going to meet in the middle, and gas exchange will happen. Okay, so your lungs, you have a right one and a left one, hopefully. On your right lung, you have a superior lobe, a middle lobe, and an inferior lobe. On your left lung, you have an inferior lobe, and you have a superior lobe. Why is there not a middle lobe in your left lung? Does anybody want to take a guess? Maybe a better question is, why is your left lung slightly smaller than your right lung? Space for the heart. Yeah, because your heart is hanging to the left, right? So you got to have a space for that. And that space is called the cardiac notch. Okay, so this is just a scoop that's taken out of your lungs that's there to give space to the heart. Okay. What would happen if you didn't make space for the heart and those two things were like pushing up against each other? I'll give it to you. Friction, and you would just tear a hole in your lungs or your heart, whichever one would fail first. Hard time pumping. Yeah, and you'd also build up a whole bunch of fluid there, right? Because it would cause an inflammatory response. So you want to create space for it, okay? All right, respiratory zone. So if air comes down the trachea, into the main bronchus, into the, let's say, left bronchus, into the secondary bronchus, and into the tertiary bronchus, and makes it all the way to this little point right there. Your terminal bronchial, right? What's going on right here? So it's surrounded by smooth muscle. Why might it be important that there is muscle here? To apparently close off this airway. Why might that be necessary? Seeing no answers, I will give it to you. Because you want to be able to control where the air is going, right? Like if there's some bad stuff going on here, you want to kind of shift that over there. So this is smooth muscle, and that controls where that air is kind of shunted to, right? If it's smooth muscle, is it voluntary? Is this a voluntary thing that you know you're doing? Ooh, smooth muscle is involuntary. All right, so the air is, let's say, the inside of this tube, right? So it's sticking out here. That's bad. All right, so it's going through here, and it ends up in this little ball right here. There should be a little ball on the end of that. That's called an alveolar space. So this is the alveolar duct. All right, well, let's just hang on. So terminal bronchial, okay? And then it goes into the respiratory bronchial. So each respiratory bronchial is surrounded by something called an alveolar sac. So like that's a number of alveoli. Each one of these little balls is alveoli. Okay, it's an alveol. Okay, there's a pore in the middle. That's where the air comes into the alveoli. And then this space right here is called the alveolar space. Okay. So alveoli, alveolus is singular, alveoli is plural. Learn your Latin. Okay. Now, gas exchange happens, and then the air gives up oxygen that goes into, it meets up with the deoxygenated blood, and it gives up its oxygen, and then it turns into oxygenated blood. Okay. And that happens in the capillaries. Okay. And then the deoxygenated blood comes from the pulmonary artery. Remember, artery is away. And then it goes into the oxygenated pulmonary vein. Venous return, arteries away. Okay, so blood goes deoxygenated to the lungs and then oxygenated through the veins. Okay, pretty simple. All right, what's happening at a cellular level? Okay, so the alveolus, each individual one, is responsible for gas exchange. So air comes in here, and it meets up with a whole bunch of cells. Okay, it's like surrounded, and it's like, "What's up, guys? This is a blob. Don't worry about it quite yet." All right, so you're gonna notice there's a couple things going on in here. Okay, so you've got a capillary where the blood's coming through. You have alveolar pores. Basically, think of like places where there's a draft. So this is where the air is coming in, and then it fills up this space. Okay. In here, you've got type 1 alveolar cells, which do something. There's also type 2. And then you've got macrophages. Why do you have macrophages in here? What's the point of that? Interactive. Give me an answer. Some of you have been tested on this already.
I missed the question.
Fish are slacking. Yes, engulf bacteria. Yeah, because the lungs are a what? What kind of defense? They're a barrier defense. Good job, Matt. Thank you. Okay, the lungs are a barrier defense. So bacteria is going to end up in here, and it can't get out of this crazy prison and then the macrophage is just going to eat it right there. There's no reason to elicit like a huge immune response because there's not a whole lot moving around in here. Either something's going to come in and the macrophage is going to need to eat it, or it's not, basically. So they're going to come in here, be like, hey guys, what's up? And then be like, oh crap, and then be eaten. Okay? Not necessarily just bacteria, viruses, also environmental stuff as well. Fun fact, I took an environmental physiology class in grad school, and that was super fun because you learn things like when people have lung disease that's based off of like living in a city, people get like debris in their lungs. It all just kind of settles, right, because of gravity. So like your left lung, just because of the way your bronchuses are, will end up with more crud in it, right? And that generally will have to be engulfed by the macrophage. And if it can't be broken down, it'll just stay there forever, right? So, which was really fun because we were dissecting people in cadaver lab, and you would be able to tell like if they lived in the greater Baltimore area or if they lived like in the city. So it was pretty cool. So we could see that. Okay. So lung pleura. Okay. So the pleura is just the layer, right? So there's different layers of the lungs. Okay. So you have, if this is a gross anatomy of a lung, not a gross lung, it's a big anatomy. You've got pleuras. So they lie within your thorax, right? Your thoracic space. You have intercostal muscles between each rib. So this is a rib, there's a muscle there. This is a rib, there's a muscle there. And then you have your sternum and your cartilage right here, right? Costal cartilage right here. Okay. And that creates a space. Okay. So there's a space within here that your lungs are taking up. Right. Now, on the interior side of your thorax, right, you've got your muscles, your bone, you've got the pleural cavity. So there is parietal pleura, okay, and then visceral pleura, and then there's a space between called the pleural cavity. There's two layers here, okay. Your parietal pleura is outside. It's touching the parietum. I don't know if that's a word. Let's see. Is it parietum? It's Latin. I know it is. What's a species of B? Okay. I don't know. It's a Latin word. It's touching the inside of the space. Okay. So whatever space is being created by ribs and muscles, parietal is always touching the space. Okay. And then visceral is touching the viscera. Viscera is organ. Okay. So you have the organ pleura and then the space touching pleura, and then there's a cavity between those two. Okay. All of this creates something called the pleural sac. So you have a layer right here that goes all the way around that protects the lung. It's not really protecting, it's just a layer of epithelium. Okay. It's shiny, so you can tell what's parietal, what's visceral. Okay. Don't click fine. This is normal and asthmatic tissue. People with asthma produce more mucus and can't breathe very well. So I guess we'll talk about that more. I mean, it's just a disease of the lung. There's lots of diseases of the lung. Asthma is just thickened mucosa, right? So like if people are having an asthma attack, their goblet cells right here are producing more mucus and they can't breathe. Go figure. It's an autoimmune response, right? You see all of this right here. So this is if you have this much space and then you add on a layer of mucus and you add on a layer of inflammation, you're closing that alveolar space. So that's bad. Okay, breathing. Let's talk about breathing. How do you breathe? Okay, so pulmonary ventilation, otherwise known as breathing. Okay, so you have two pressures that are working. We're going to talk physics now, and we love physics, which is why we took anatomy. So you have atmospheric pressure and then you have intra-alveolar pressure, okay? So those two pressures are fighting against each other, okay? So alveolar pressure, it changes during the phase of the cycles, but it equalizes at 760 millimeters of mercury. So sometimes it's less, sometimes it's more, okay? So and this is all mediated by one thing, okay? Your lungs are not actively contracting and expanding, right? They're not acting on their own. That smooth muscle is not for the lungs to expand and contract. What's causing expansion and contraction is negative pressure within the thoracic cavity, okay? And that is caused by the diaphragm. So you are not breathing into a balloon and the balloon expands and contracts, okay? What's happening is you're putting the balloon in a vacuum chamber that creates a vacuum on the balloon and inflates it and then relaxes and lets it deflate, okay? Don't get that confused. Your lungs, there's no active motion in your lungs. What's happening is your diaphragm is creating a vacuum, negative pressure on a vacuum, and that's expanding the balloon of your lungs and letting physics happen naturally, okay? So gas exchange is not like an active process that you're like, oh, I need more gases, I need to make my lungs bigger. You mediate that by control with your diaphragm and your intercostals. There's actually 4 muscles that control breathing, but your diaphragm is the big one, okay? All right, so you have this pressure right here. That is your transpulmonary pressure. And then you have your intrapleural, or it's your intrapleural pressure. And then you have your transpulmonary pressure, okay? So if atmospheric pressure is, what is it? Mercury. Okay. If atmospheric pressure is 760 millimeters of mercury, I wish I could write on this. That'd be so easy. You're gonna have plus or minus 4 millimeters of mercury. So here, when your diaphragm is expanded, you're gonna have 156 millimeters of mercury, and then on the inside of your lungs, you're gonna have plus 4, right? So it's gonna be 764. Sorry, not great at math, but we're gonna do physics. Okay, so does that make sense to everybody? Is there any questions about like how you breathe? Let's keep it simple. Your diaphragm pulls on a vacuum chamber and it opens up your lungs and creates negative pressure on your lungs that they will expand. Okay. It's not like blowing a balloon up. Okay. So Boyle's law. That was better. Thank you. All right, Boyle's law. So as volume decreases, right, pressure increases. So if you decrease the volume, if you increase, and it also works in reverse, right? So if you increase the volume, right, pressure will decrease. So if you decrease the pressure, volume will increase. Inverse, right? Or directly proportional, right? Right here. Okay, so if you increase the volume, pressure decreases. As you decrease the volume, pressure increases. So think of this as I'm inhaling, the volume is increasing, and the pressure from my diaphragm is decreasing the intrathoracic pressure, okay? And then I'm relaxing my diaphragm. I'm not blowing out, I'm relaxing my diaphragm. And that is increasing the pressure on my lungs and decreasing the volume, okay? So gas goes in, and then it's all relative to atmospheric pressure, okay? So as you expand, the intrathoracic pressure, the pressure within your lungs is decreasing as well. Okay, so you're drawing air in. It goes from an area of high pressure to low pressure. It's a pressure gradient. Okay, I don't know how many times I can say pressure in this without losing you completely. But you're going from area of high pressure, atmospheric, to an area of low pressure because you have decreased the pressure and your volume increases. The air is moving into your lungs. And then as you relax your diaphragm, you're decreasing the volume and increasing the pressure on your lungs. So the air is moving from high pressure to low pressure. We're talking about teeny tiny, little tiny changes in pressure. And those little changes in pressure are enough to mediate what's the word I'm looking for? To mediate gas exchange within your alveoli. Okay. All right. This is everything I just said in the picture. I really wish I would have clicked on this next. Okay. So inspiration, your thoracic cavity expands. You also contract your external intercostal muscles, right? So your ribs, instead of this much space, they're going like this, and they're creating space for your lungs to expand. And all of that is mediated by the diaphragm. So your diaphragm is going to contract. So if the diaphragm looks like this, right? If these are muscle fibers, they're going to contract, and then your diaphragm is going to go down. Okay. Your lung is going to fill that empty space, and it's going to open up. Okay. And then your diaphragm will relax, right? So it'll contract and then relax. And then your diaphragm fills that empty space and your lung squeezes up a little bit like a sponge. Okay. The other thing too is your lungs look like a sponge. They're not like balloons. Like you can't just like pop one and be like popping a sponge. So they're very spongy and they're squishy. And you can squeeze them and little bubbles come out sometimes. Okay, so your lungs, that's what's happening here. As you exhale, your thoracic cavity reduces instead of expands, and your external intercostal muscles relax. Okay, so your ribs go from, so you're increasing the space between your ribs, you're decreasing the amount of space in your thoracic cavity, and your diaphragm relaxes as well. Okay, so are your lungs mediating this process? Are they just blowing up and down? No. They are a passive result of this function. Okay. This happens, they are not in control of the situation. Okay. All right. Normal atmospheric is 760. Yeah, well, I could have just clicked. Okay, I really gotta start preparing for these better. All right. So millimeters of mercury is mmHg. A normal atmospheric pressure is 760. Torr is 1 millimeter mercury. It's the exact same thing, but named after a white man. So this is 760 torr equals 760 millimeters of mercury. Okay. Centimeters of water is like stupid uncommon. Please don't ever use this. I'm never going to ask you to use it. And then PSI, pounds per square inch. So atmospheric pressure at sea level is about 15 PSI. So we generally won't use PSI as much when calculating the difference between pressure gradients in your lungs. Normally it's just going to be millimeters of mercury or if we feel like being lazy. All right, so factors affecting the pulmonary ventilation. Surface tension. How much are those epithelium that are in your alveoli, how much are they trying to hang on to each other? Okay. Are they sliding real smooth or are they locked in place? Okay. That is all controlled by surfactants and mucus. Okay. So you have surface tension between the individual cells. Compliance, which is basically another word for are your lungs actually like helping in this process? And then airway resistance. So that could be because of inflammation within the airway. It could also be because there's something in the airway or asthma, right? All right, pulmonary volumes and capacities. So if you're just sitting here breathing, this is your tidal volume. Let's focus on this for a minute, okay? At any given point, you have tidal breathing, okay? And that's just, or tidal respiration, I guess I should say. So that's happening right here. And I know what you're thinking. How much air is in your lungs, or how much can they hold? The answer is about 6,000 milliliters. Okay, it's a ton of air. 3 2-liter bottles in a normal person. Okay, so your tidal volume, and at any point you're keeping about half of that volume. Okay, so if I'm just sitting here doing nothing, hanging out, my tidal volume when I breathe in is about 3,000 milliliters or 3 liters. And then when I breathe out, it's about 2,500 milliliters or 2.5 liters. Okay, so 3 liters, 2.5 liters. Okay, that was a little exaggerated, so probably a little bit more. Okay, all right, so that's chilling. That's your tidal volume. Okay, now if I'm going to take a deep breath all the way up to here, this is my maximum inspiratory capacity. Inspiratory capacity. Okay, so this is the most amount of air that I'm going to breathe. Okay, that is from the bottom of your tidal volume. So let it out and then all the way in. That's inspiratory capacity. And I hope you're all doing this at home and looking just as silly as I am. Okay, the space between the maximum of your tidal volume and your inspiratory reserve volume, or in your capacity, is called your inspiratory reserve volume. So this is how much gas or how much air your lungs could breathe in if they had to, right? That's the reserve volume. Okay. All right. So let's see. Total lung capacity. Yeah. So this total lung capacity is the whole kit and caboodle from 0 to 6,000. Okay. Your inspiratory capacity is from the bottom of your tidal volume all the way up to the top of your reserve volume. Okay. Now, if I want to take a deep breath out, that is called your expiratory reserve volume. And that volume is calculated from the bottom of your tidal volume all the way down until you start coughing. Okay. That's your expiratory reserve volume. That's how much air you can force out of your lungs. Okay. Now, because you can't squeeze your lungs all the way, right? Your diaphragm doesn't go up into your throat. It stops. It goes like from here. I don't know if you can see that. From here to like here. Okay, it's not like super big, so it's pretty big, but it doesn't like do a whole lot. Okay, you can't just like squeeze it all away. Everything that's left over is called residual volume. Okay, so you have about 1,100 milliliters of residual volume. From 1,100 all the way up to about 2,500. That's your expiratory reserve volume. And then your tidal volume floats around here. And then your inspiratory reserve volume goes all the way up to the top. Okay. So if you were to start here at the bottom of your tidal volume and just start exhaling, this is called your functional residual capacity. Okay. This is how much air is going to be in your lungs if you need it. Okay. This is how much air will contribute to gas exchange. Okay, so you can breathe all the way out and still exchange gas because you have a residual volume. It's not going to be super efficient, but you could do it. Okay, your vital capacity. So all the way in to all the way out is your vital capacity. And that is generally 1,100 to 6,000. So that makes it 4,900 milliliters of air. Okay. And that's your inspiratory reserve volume plus your expiratory reserve volume plus your VT is something tidal volume. Yeah. So your functional reserve, inspiratory reserve, and then tidal volume. That is your vital capacity. Okay. And then all of that makes up your total lung capacity. Okay. Capiche? Great. You're gonna need to know all these terms. Not like crazy in depth, but just be able to like recognize them. Okay. So if I give you like your functional residual capacity, that's the volume of air left in the lungs after normal expiration. Okay, so that's that. Okay. Your expiratory reserve volume is the volume that can be exhaled beyond normal exhalation. So all the way to coughing. Okay. Your forced expiratory flow. So that's what your airflow in the middle of exhalation. So it's like how much, like what percent of your air are you forcing out? So it's usually 25 to 75%. So peak expiratory flow is the rate of which you're exhaling, right? So you have volumes and then rates, right? So your breathing rate is supposed to be normal, okay? And you can control pretty much all of those except for residual volume, okay? All right. So meeting oxygen demands. So let's calculate your respiratory minute volume. Doesn't that sound so fun? All right, so if your volume of air moved each minute equals F, which is breaths per minute, times tidal volume, okay? So you're just taking all of these over the course of a minute and adding them up, okay? Pretty easy. So if your normal respiratory rate is 12 to 18 breaths per minute, multiply that by your tidal volume, you get your respiratory minute volume. Why is that important? Because one day you might be really into cave diving and you need to know what your respiratory minute volume is so you can calculate how much gas you're breathing in the tanks that you are breathing underwater. But if you're not like me, then you don't really need to know that. All right, alveolar ventilation is breaths per minute times tidal volume minus dead space 150. So there's also a little bit of dead space at the end that is just never gonna do anything. Okay, so you're just tracking that. That's really it. You need to know for like calculations. Okay. How's all this controlled? What's going on? Who's in charge here? Okay. All right. So if your lungs are not receiving direct stimulation from the nervous system, what is controlling them? Well, I'm glad you asked. It's your diaphragm. Oh, hang on. It's your diaphragm. So your diaphragm has neurons to it, okay? So the main center of respiratory control lies in your pons. So this is in your brain. You have a pneumotaxic center, an apneustic center, and this is called your pontine respiratory group, okay? This is positive control and negative control, okay? So if you're giving negative feedback to your dorsal respiratory group, which is different DRG than dorsal rama or dorsal root ganglion, and then you have positive control through your apneustic center, okay? So positive apneustic, negative pneumotaxic. Think like taxing the pneumo system. I don't know if that helps. And that is all control. The positive control goes to your ventral respiratory group. So ventral is like front, dorsal is back, right? So if your dorsal respiratory group is going to your back, it's giving stimulation down here into your diaphragm, right? Where external intercostal muscles, because your nerves wrap around your back. Think of don't think of anything. Just know that the dorsal respiratory group controls your diaphragm and your external intercostal muscles. Okay. And all of this is controlled through C3, C4, and C5. And if you need help remembering that, it's C345 keeps the diaphragm alive. All right. So then you also have your ventral respiratory group, and that goes to your internal intercostal muscles. Your internal intercostals are just the space between your ribs. So it's getting that last little bit of rib space. So this only really happens during like extreme exercise or like really need some air. Okay. All right. So this is all involuntary, by the way. Like a little bit of voluntary, but mostly involuntary. Okay. So you have things that affect that. So you have chemoreceptors, baroreceptors, and stretch receptors. Okay. So chemoreceptors. So you have receptors in your bloodstream that are picking up the pH, the O2, and the PCO2 of the blood. Why are we looking at the CO2 of the blood? Any guesses? Best guess. All right, I'll tell you. You can beat it out of me. Okay, so you're looking at PO2 and PCO2. The reason for that is O2 binds to hemoglobin. CO2 does not bind to hemoglobin. It is dissolved in the bloodstream. Okay, so if you have a lot of CO2 in the bloodstream, it's dissolved in there as an acid, right? And so your blood will become slightly acidic. So there could be reasons why your blood is acidic. It doesn't always have to be PCO2, but it could be. So we're going to have chemoreceptors for pH and PCO2. When those things both trigger at the same time, we go, oh crap, we're having a breathing problem. Okay, we need more oxygen. So that will stimulate you to either breathe more or breathe deeper. Okay. So these all kind of work in concert, all right? And your PO2 is just the saturation of oxygen. All right. So you're able to kind of tell that too as well. All right. You also have baroreceptors. So changes in blood pressure will also influence whether or not you need to breathe more. Okay. So if your blood pressure goes up because you're I don't know, you're having like an activity of sorts, you're having a shindig, right? Your blood pressure's going up. That's going to trigger those baroreceptors to be like, okay, well, our pressure's up, and we're not. That's going to throw off the balance of our pressure gradient of our ease of breathing, so we need to adjust accordingly. Okay. And then you also have stretch receptors in the lung that changes. They respond to the changes in the volume of the lung, and those are responsible for inflation and deflation reflexes. So like if you need to like cough or something like that, stretch receptors. Okay. In addition to all of this, you have physical or chemical stimuli in the nasal cavity, larynx, or bronchial tree that initiate protective reflexes such as coughing and sneezing. So when you cough or sneeze, it's because something got picked up in your nose and it's like, get it out, right? So you'll sneeze, or something gets kind of trapped in your trachea, and the little cells on the inside of your trachea go, get it out. So they'll cause you to cough. Okay. Sometimes it's just easier to cough crap out. Sometimes you want to eat it by macrophage. So it just, all of that stuff kind of happens. So it varies. Okay. Gas exchange. How much time do we have? 10 minutes. Let's see. 35 to 44. This is tough. What do I want to do? Let's pick up our gas exchange next time because I want to have some time to talk about it. But I promise we won't get too far behind. All right. Questions? Anybody have any questions? How are we feeling? Good. Awesome. Lungs are easy. Lungs are pretty straightforward. It's just pulling the diaphragm down. That's all. Yeah, there's no crazy like complementary pathways or anything like that. You already learned all the hard stuff. So not really. much more to go. But yeah, lungs are pretty straightforward. Same thing with heart, like it's heart lungs, like same thing. It's just pressure gradients and moving stuff around. So, yeah. All right. Well, I'll be here. If you guys have any questions, I'll hang out. If not, I'll just cancel or I'll end this in a few minutes.